signatures of design. The study of physical reality often requires a technical analysis of biological and cosmological complexity to understand the underlying principles of existence. This investigation focuses on evaluating the explanatory power of undirected material processes compared to the potential for intentional agency in the formation of the universe. For engineers, this is akin to reverse engineering a sophisticated system to determine if its specifications arose from a series of accidental events or a deliberate blueprint. By examining the intricate data sets found in the natural world, we can apply rigorous analytical frameworks to determine the most likely origin of these complex structures. Biological systems and the overarching laws of physics exhibit a level of organization that demands a precise causal explanation. As we delve into the signatures of design, we move beyond mere observation and into a structured evaluation of how functional information is generated and maintained. This approach considers whether the high-level coordination seen in cellular machinery and universal constants aligns better with stochastic processes or an engineering model. Through this lens, the presence of intentional agency becomes a primary hypothesis that can be tested against empirical data and mechanical principles. The emergence of a third paradigm. Intelligent design operates within the sphere of empirical science by challenging the sufficiency of undirected material processes through a rigorous evaluation of biological and physical data. This paradigm shift represents a move toward a more integrated engineering model that views functional information as a primary constituent of reality. In this framework, the core mechanism is identified as intelligent agency rather than a standard neo-Darwinian reliance on random mutation and natural selection. This approach allows researchers to analyze the origins of life and the cosmos using the same logical tools applied to human-made technologies. When comparing neo-Darwinian macroevolution to intelligent design, we find diverging philosophical bases and complexity models. The Darwinian view relies on methodological naturalism and materialism, positing a bottom-up gradualist assembly where information emerges from undirected processes. Conversely, the design paradigm utilizes an inference to the best explanation, known as IB, which views information as requiring an intelligent source. This perspective treats complexity as a product of top-down integrated engineering, suggesting that high-order systems are the result of specific foresight rather than incremental, unguided steps. Diverging methodologies in historical science. When analyzing high-order functional information and integrated machinery in the living cell, uniform experience demonstrates that these effects are invariably the product of intelligent agency. Intelligent design does not proceed from religious authority, but functions as a minimalistic theory positing a designer based purely on the informational properties of nature. It utilizes standard cause and effect reasoning to interpret data gathered from the natural world. This methodology allows for a neutral investigation into the origins of complexity without the constraints of a purely materialist worldview. In historical science, there is a clear distinction between methodological naturalism and the inference to the best explanation. Methodological naturalism dictates that science must only invoke material causes, essentially locking the door to any non-material explanation, regardless of the evidence. However, the inference to the best explanation is the standard used in fields such as paleontology, forensics, and the search for extraterrestrial intelligence, or SETI. By using this standard, we can recognize that certain patterns and functional systems are most reasonably attributed to an intelligent cause. The explanatory filter. Intelligent design uses a rigorous process of elimination method known as the explanatory filter to determine the most reasonable cause for a given phenomenon. This filter is a three-stage logical tool used to distinguish between natural laws, random chance, and design. At stage 1, we evaluate regularity and necessity by identifying high probability, law-like behaviors such as gravity or crystal formation. If a phenomenon can be explained by these consistent physical laws, the search for a cause ends there. This ensures that we do not mistakenly attribute standard physical interactions to higher-level design. If a phenomenon cannot be explained by regularity, it moves to stage 2, which assesses the role of chance. This stage looks for intermediate or random probability events that are stochastic and lack any recognizable functional pattern. If the event is still unexplained, it reaches stage 3, which focuses on design by looking for low probability combined with specification. This combination describes highly improbable events that conform to an independent pattern, such as the digital code in DNA, computer software, or human language. This systematic approach ensures that design is only inferred when chance and necessity are statistically insufficient. Information theory and the digital code of life. The digital code of life is a profound example of information theory applied to biological systems, where DNA stores data at a density of 2 bits per site. This confirms that the universe comprises matter, energy, and information as its fundamental building blocks. Just as the laws of chemistry do not dictate the order of nucleotide bases, the chemistry of ink does not dictate the words in a book. The physical medium facilitates the message, but does not generate the semantic content itself. This distinction is critical for engineers who understand that hardware alone cannot create software. Cells utilize advanced, computer-like systems such as nested coding and distributive retrieval, which are universally recognized hallmarks of high-level engineering. These systems allow for the efficient storage and access of vast amounts of functional data required for life. The presence of such sophisticated information processing indicates that the source of this data must be capable of generating complex specifications. By treating biological information as a digital entity, we can apply quantitative measures to determine the probability of its origin. This analysis highlights the gap between undirected chemical interactions and the precise orchestration of the genetic code. The challenge of irreducible complexity. Irreducible complexity describes a system composed of several well-matched, interacting parts that contribute to a basic function. In such a system, the removal of any one part causes the system to effectively cease functioning entirely. This presents a massive hurdle for Darwinian evolution, which relies on functional advantages at every intermediate stage of development. If a system is non-functional until all parts are present and integrated, it cannot be built by natural selection through gradual steps. The lack of a functional halfway measure means the intermediate stages would be discarded by selection. We can visualize this challenge by comparing a Darwinian assembly to an interdependent structure like an arch. A Darwinian assembly is like a set of stairs where every step is functional and provides a measurable advantage. However, an irreducibly complex system is like a stone arch where the keystone and the supporting blocks must all be present simultaneously for the structure to stand. Without the complete set of parts, the system provides no function and offers no selective benefit to the organism. This suggests that such systems must have been assembled as a complete, integrated unit from the outset. Case study: the 100,000 revolutions per minute rotary motor. The bacterial flagellar motor is a biological masterpiece capable of rotating at 100,000 revolutions per minute with near 100% energy efficiency. This rotary motor is composed of multiple specialized proteins that function together like a mechanical engine. For an engineer, the complexity of this system is staggering, featuring parts that correspond directly to human-made motor components. Co-opting these parts from other systems would require massive, coordinated multi-mutation leaps, presenting an irreducible hurdle for any gradual origin theory. The sheer precision required for assembly and operation points toward a top-down design process. The motor consists of a FLF-MS ring, which acts as the central hub, and MOTA and MOTB proteins that serve as the stator. The rotor is formed by the FLG, FLIM, and FLIN searing complex, which translates electrochemical energy into mechanical torque. To facilitate movement, the FLG hook acts as a universal joint, while the flick filament serves as the propeller. Additionally, the FLGI and FLGH proteins provide the necessary bushings for the rotating drive shaft. The integration of these specific parts into a high-speed, high-efficiency machine is a clear signature of sophisticated engineering. Case study: the eukaryotic axoneme. The modal cilium is a complex cellular structure that generates movement through an all-or-nothing interdependent triad of components. This system, known as the axoneme, relies on the precise coordination of microtubules, dynein arms, and Nexon linkers. Microtubules provide the structural scaffold and tracks for movement, while dynein arms are motor proteins that convert ATP into mechanical sliding. Removing the fibers, the motors, or the linkers instantly neutralizes the function of the cilium. This immediate loss of utility disproves a gradualist origin path where parts would need to wait for their counterparts to appear. Nexon linkers are elastic proteins that convert the sliding motion of the microtubules into functional bending, which is what allows the cilium to propel the cell. Without these linkers, the dynein arms would simply slide the microtubules past each other without creating any useful movement. The entire system must be present and correctly aligned to provide any selective advantage to the organism. This case study demonstrates how biological systems often require a complete set of integrated parts to perform a single basic function. For engineers, this level of interdependency is a hallmark of intentional, top-down design. Case study: integrated biochemical cascades. Vertebrate blood clotting requires a precisely timed sequence of enzyme activations to form a clot at an injury site while simultaneously preventing lethal systemic clotting. This is an engineering hurdle because homologous proteins do not explain the selective pathway required to integrate non-clotting precursors into a flawless cascade. The system must be fast enough to stop a bleed, but controlled enough to avoid clotting the entire circulatory system. Each step in the pathway serves as a prerequisite for the next, forming a highly integrated biochemical circuit. Missing a single factor in this chain leads to catastrophic system failure. The cascade involves a series of transitions, starting with factor 3, also known as tissue factor, and factor 7. These activate factor 10, which in turn leads to the activation of factor 2, moving from prothrombin to thrombin. Finally, factor 1 converts fibrinogen into fibrin to form the structural mesh of the clot. A critical failure point is found at factor 8. A deficiency here leads to the condition known as hemophilia. This interdependence highlights the necessity of having every component of the cascade present and functional from the beginning to ensure the survival of the organism. Mathematical constraints and the waiting time problem. The waiting time problem addresses the mathematical limitations of the neo-Darwinian mechanism in generating vast genetic information within available geologic time. We can express this using the formula: T is approximately 1 over R. In this equation, T represents the waiting time, and R represents the rate of mutation. Douglas Axe's models of stochastic tunneling demonstrate that the creative power of random mutation is severely constrained by the sheer scale of the search space. When we analyze the time required for specific, coordinated changes, the numbers often exceed the age of the Earth. Calculations show that the waiting time for just 2 coordinated mutations in a primate population is greater than 216 million years. This far exceeds the available geologic time provided by the fossil record for the transition between many species. The gap between the evolutionary requirement and the time actually available suggests that undirected processes are insufficient to account for the emergence of new life forms. This mathematical constraint forces us to look for an alternative explanation that can account for the rapid appearance of functional information. For engineers, this is a clear indication that the system did not arise through a trial-and-error process. Cosmological fine-tuning. The universe is characterized by a level of precision that is difficult to overstate, particularly regarding the cosmological constant. This constant is set to a precision of 1 part in 10 to the power of 120. Any significant deviation from this value would cause the universe to expand too fast for matter to coalesce or collapse too soon for life to develop. This is one of several fundamental constants of physics that are set within incredibly narrow, life-permitting ranges. This level of fine-tuning suggests that the parameters of our universe were intentionally calibrated. Other examples of fine-tuning include the strong nuclear force and the balance between gravity and the electromagnetic force. A small deviation in the strong nuclear force would mean the universe contains either no hydrogen or only hydrogen, precluding complex chemistry. The ratio of gravity to the electromagnetic force is tuned to 1 part in 10 to the power of 40. Any change would cause stars to burn out instantly. Most impressively, the initial entropy of the universe is tuned to 1 part in 10 to the power of 10 to the power of 123. Such extreme precision resulting in a structured universe strongly points to a design rather than a chaotic origin. Paleontological discontinuity, the Cambrian explosion. The Cambrian explosion was a biological event that occurred approximately 530 million years ago and lasted only 10 to 20 million years. In what is described as a geological blink of an eye, between 20 and 35 major animal phyla appeared abruptly. This biological Big Bang occurred with no clear ancestral precursors in the earlier fossil record, generating the massive amount of biological information required for fundamentally new body plans overnight aligns with an engineering model rather than random mutation. This sudden emergence of complexity challenges the idea of a slow, bottom-up divergence. While the Darwinian prediction suggests the bottom-up gradual divergence of species, the fossil record actually shows a top-down sudden emergence of phyla. We see the immediate appearance of complex groups such as arthropods, chordates, echinoderms, mollusks, and platyhelminths. Other distinct forms like annelids, cnidarians, porifera, brachiopods, nematodes, priapulids, and onychophorans also appear without transitional links. This pattern of sudden arrival and subsequent stasis is consistent with the deployment of pre-engineered designs. This paleontological discontinuity suggests that the information for these body plans was introduced rapidly into the biosphere. The convergence of evidence. The case for intelligent design rests on the alignment of disparate scientific fields that all point toward a common conclusion. At every scale of reality, from macroscopic cosmology to microscopic biochemistry, the data points to the inadequacy of undirected material processes. We find evidence of an intelligent cause in the digital information stored in DNA and the irreducibly complex machinery of the cell. Mathematical limits regarding waiting times and the extreme fine-tuning of physics further support this inference. Finally, the fossil record's Cambrian discontinuity provides a historical snapshot of sudden, top-down emergence. When we view these different lines of evidence together, they form a robust and consistent framework for design. Digital information, irreducible complexity, and mathematical constraints are all independent indicators of intentional agency. In engineering, when multiple independent subsystems all point to a single architectural source, we recognize it as a unified design. This convergence indicates that the origins of life and the universe are not the result of isolated accidents, but part of a coordinated whole. By integrating these scientific fields, we can move toward a more comprehensive understanding of our intelligible universe. An intelligible universe. Intelligent design is not a theological deduction. It is a legitimate scientific inference drawn from the ultimate engineering found in the natural world. The informational and teleological properties of our universe strongly indicate that life is the product of an intentional mind rather than a mindless process. This perspective shifts our understanding of nature from a series of random collisions to a structured system with recognizable purposes. By applying engineering principles to the study of the cosmos, we can identify the hallmarks of design with greater clarity. This approach respects the data while remaining open to the best explanation. The universe appears to have been designed not only for the existence of life, but to be intelligible to the human mind. Our ability to discover and understand the laws of physics and the complexities of biology is a profound characteristic of our reality. This correspondence between the structure of the world and our cognitive faculties points to a deeper level of intentionality. As we continue to explore the technical details of the natural world, the evidence for a designer becomes increasingly difficult to ignore. Recognizing the intelligibility of the universe is the first step toward understanding the mind behind the design.